Greetings to the respected faculty. I am Lasya Mandapati, a student from the CSC AI&ML department, and my roll number is 24951A6686. Today, I'll be presenting an overview of the topic Types of Crystal Structures. It's a fundamental topic in our Applied Physics course. We'll delve into the fascinating world of how atoms arrange themselves in solid materials and why this arrangement is so crucial. Let's begin our exploration. So, what exactly are crystals? At their core, crystals are solid materials where atoms, molecules, or ions are arranged in a highly ordered, repeating three-dimensional pattern extending throughout the material. Understanding these crystal structures is paramount because they dictate a material's fundamental properties. The way atoms are arranged in a solid directly influences its mechanical strength, electrical conductivity, optical behavior, and so much more. The basis for classifying these structures lies in the concept of the unit cell. Think of a unit cell as the smallest repeating unit that, when stacked together in a three dimension, creates the entire crystal lattice. These unit cells come in various shapes and sizes, leading to different types of crystal structures. We'll be exploring these different types today and also touching upon the diverse applications of crystalline materials and that we encounter in our daily lives, from the silicon in our electronics to the metals in our infrastructure. Let's start with one of the most symmetrical and common crystal structures, the cubic crystal structure. As the name suggests, its unit cell is the perfect cube, with all sides in equal length and all angles at 90 degrees. The structure is particularly prevalent in many metals we use regularly, such as copper and gold. With the cubic system, we find three main varieties: simple cubic, SC, where atoms are located only at the eight corners of the cube; body-centered cubic, BCC, which has additional atoms positioned at the very center of the cube; and face-centered cubic, FCC, where uh, in addition to the corner atoms, there's an atom located at the center of each of the six faces of the cube. FCC and BCC structures generally exhibit a high coordination number, meaning each atom is surrounded by a large number of neighboring atoms, leading to high packing efficiency. The atoms are packed relatively close to each other. Moving on, we have the hexagonal closed packed structure, HCP. This structure is characterized by a hexagonal arrangement of atoms in its layers, with a specific stacking sequence of these layers, typically described as ABAB stacking. Let me explain in detail. Imagine one layer of hexagons A, then another layer B, fitting into depressions of the first, and then a third layer A directly above the first. HCP is common in metals like zinc and magnesium and is known for its high density packing, similar to FCC. However, it possesses lower symmetry compared to cubic structures. In HCP, each atom is surrounded by six atoms in its own layer, and three atoms each in the layers above and below, totaling 12 close neighbors. The bonding in HCP structures can often exhibit strong directional characteristics, and these materials find significant applications in the aerospace industry due to their strength to weight ratio. Now, now, let's consider the tetragonal crystal structure. Think of it as a cubic structure that has been stretched or elongated along its axis. So, while two of the axes remain equal in length, all angles are still 90 degrees, the third axis is either longer or shorter. A common example of the material with a tetragonal structure is white tin. Similar to the cubic system, we have two main systems of tetragonal unit cells: simple tetragonal and body-centered tetragonal. Due to the elongation along one axis, tetragonal materials often exhibit anisotropic properties, meaning the properties differ depending on the direction in which they are measured. The atomic packing in tetragonal structures is often or generally different from cubic structures, and they possess lower symmetry. These materials find applications in electronics due to their unique electrical and magnetic characteristics. Next, we have the orthorhombic crystal structures. In this system, all axes of the unit cell are of unequal lengths, but importantly, all the angles between these axes are still 90 degrees. This structure is found in various materials, including sulfur and the mineral olivine. Within the orthorhombic system, there are four possible Bravais lattices: simple, base centered, body centered, and face centered, each with a different arrangement of atoms within the cell. These different arrangements lead to varying moderate packing densities. The orthorhombic system is less symmetric than the tetragonal and cubic system and is particularly important in the study of minerals due to the prevalence in geological formations. Moving towards lower symmetry, we encounter the monoclinic crystal structure. Here, two of the angles between the axes are 90 degrees, but the third angle is not 90 degrees. Additionally, all three axis lengths are generally unequal. Examples of materials with a monoclinic structure include gypsum and mica. There are two types of monoclinic units: as simple, also known as primitive, and base centered. The low symmetry in the system leads to a more distorted atomic arrangement compared to the higher symmetry systems we've discussed. Monoclinic materials are used in ceramics and play a key role in geology, particularly in the formation and properties of various rocks and minerals. Now, we arrive at the crystal system with the lowest possible symmetry, the triclinic crystal structure. In this system, none of the axes are equal in length, and none of the angles between the axes are 90 degrees. An example of the material with triclinic structure is the mineral kyanite. The atomic packing in the crystal structure is often quite complex, leading to a low packing efficiency. This type of structure is relatively rare in nature. However, materials with triclinic structures can find specialized industrial applications where their unique anisotropic properties are beneficial. Our penultimate crystal system is the rhombohedral structure, also sometimes referred to as the trigonal system. In this case, all three axes of the unit cell are equal in length, but the angles between them are not 90 degrees, and all three angles are equal to each other. Examples of the materials exhibiting this structure include calcite and quartz. The rhombohedral structure can be thought of as a symmetrical but distorted cubic structure, as it possesses immediate symmetry compared to the systems we've discussed. Materials with this structure are often used in optical devices due to their birefringence properties and can find application in piezoelectric devices. Understanding the rhombohedral structure is important in crystal studies, particularly in mineralogy and materials characterization. These are the structures of the cubic cells we've discussed, which include simple, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. Moving on, now that we've explored the individual crystal systems, let's take a moment to compare them. We've seen the significant differences in symmetry, ranging from the highly symmetric cubic system to the least symmetrical triclinic system. This difference in symmetry directly impacts the packing efficiency of the atoms within the structure, with high symmetry often correlating with denser packing. The atomic arrangement types also vary significantly between the systems, leading to a wide range of applications specific to each structure. For instance, the high packing density of FCC and HCP metals contributes to their mechanical strength, while the unique structures of materials like quartz or rhombohedral enable their use in optical and piezoelectric applications. We also see density variations, differences in mechanical properties, influences on electrical conductivity, and impact on thermal behavior, all stemming from the fundamental arrangement of these atoms in these various crystal structures. The study of crystal structures is absolutely fundamental in applied physics. As we've touched upon, it profoundly affects mechanical strength, how material resists deformation and fracture. It also influences electrical conductivity, determining whether a material is a conductor, insulator, or a semiconductor. Furthermore, crystal structure determines thermal expansion, which is crucial in designing structures that can withstand temperature changes. The arrangement of atoms also governs optical properties, dictating how light interacts with material. Understanding crystal structures guides alloy development, allowing us to engineer materials with specific desired properties. It is essential for ceramic research, where Microstructure plays a critical role in performance, and it's key for semiconductor design as the crystal lattice influences electronic band structure. Even in the realm of biomaterials, the crystalline or amorphous nature of a material can significantly impact its biocompatibility. In conclusion, the crystal structure of a material fundamentally defines its properties. The classification of these structures is based on the geometry of their unit cells, the smallest repeating unit. Generally, high symmetry often correlates with higher packing efficiency and influences properties like strength and conductivity. The diverse range of crystal types allows for a vast array of materials with tailored properties for different applications, spanning from structural components to advanced electrical and biomedical implants. The ongoing field of research in crystallography continues to deepen our understanding of these structures and enables the discovery of new materials with novel properties. This fundamental knowledge is vital for engineers and technology across numerous sectors, and the study is critical for multiple industries during innovation. Thank you for your attention. I hope this overview has provided you with a clear understanding of the fascinating world of crystal structures.